You what?
We want to know about the Wasatch Fault.
I don't know what it is about the mouse. I can't make
That's
the mouse
another
on the
talk.
back work.
Teton's another talk.
It's so.
I'm going to do so many.
Yeah, geez, we were trying to get up there just to click off the shear.
Oh, hi, young lady.
Oh, good to see you. I could do
Yeah.
it on this.
Well, it's done.
Is it gone now?
She's done it. She's done it.
That's my memory.
Yeah.
I saw him come in.
We wouldn't miss this for anything.
Okay.
Okay.
Ollie, oxen free.
Here we are. Got it. She's got it.
So I think you need to click got it up there.
Say again?
Click got it up there.
It's not.
Recording.
Oh, yeah.
Yep, got it.
Just hit got it.
I can sit down, can't I?
You absolutely. You're going to be standing for the next while. So
Where are we going?
so am I
Hi,
using the
how are
recording
you?
mic or not? I don't care. I can project.
Project.
Okay.
Yeah, I think I'll get one. I think we're gonna be a while.
Get a count of everyone
just-
here and then give that to Cynthia.
Okay.
It's my new knees. I can sit here and give my talk,
I'm going to start right at 6.
right? Yeah, you can.
So I guess I'm not using tutorial mic.
Well, it does work. It's just so low. That if you put it right to your mouth,
I don't need.
but it does work. It does work.
What?
Most everybody's doing Zoom.
Oh, I'm sure they are.
So these boxes not these people could move closer to Bob.
Well, I know my crew's doing Zoom and Janet's doing Zoom in a hot hotel in Las Vegas. Well, I'm glad they got it sorted out.
It's a good thing we got here early.
That's exactly right. I recognize a lot of faces.
What? No.
No, they're all on Zoom. How many did you say?
My computer also do the lights. Or you can do one side and Mike can do the other, whatever, as long as we get them done.
We have to do 7
Yes, yes, yeah. It's just all one.
TC.
Yeah.
Jackson Hole time is 5:10.
She isn't, but she will be. She's on her way. She'll be here in a minute. Yeah. But I'd like a lot of these things.
Right.
So David right here, he's a Gene Humphrey student.
I can hear you through this computer over here. I can hear you through this computer over here.
You're muted, right?
Yep, I
No,
think
you're
so.
not.
Oh, I can do that one.
You
Okay.
gotta mute yourself.
Okay, Bob needs to
Cynthia,
share his
can I
screen
start?
again. Yes.
Bob, you want to share your screen? Yeah. And
Stop. Yeah, you're
which,
okay. Share. Just
Oh.
go to share.
okay.
Oh,
What?
Well, you don't want system preferences. I don't know what you did.
Hey, Mike, what are all these things on the screen? What are all these things on the screen? Mike, what are all these things on the screen and how do I get rid of them? I'm trying to share Bob's.
Well,
That's on my system.
we want to share his screen now, okay?
Yeah, we are. That's what I did. And then I know all this came up.
Say again?
Share.
You may have to do something. Let me keep looking at this. Somebody has to grant permission for something.
And I want you here to share.
Well, you want to get to the, you have to pick it off.
Oh,
I think Mike, you just shared that. He's got his security threats.
Okay, can you click on that all the way up
You
there?
did that once already.
Well, you have to do it again.
Yeah, you can close that. Just go up and hit the red button.
Okay, well,
Let him. He knows how to work that.
trouble is, I'll get rid of that. Where I was the last time. We're quick. We did it already. Just minimize it.
Have an error message right.
Say again? Oh, that's a good question. It's over on the right side. It's over here somewhere.
Minimize, we can minimize these guys by hitting
Yeah.
that.
I have to take a look.
Yellowstone locksmith. is that it?
Yeah, try there. Try that.
Oh, that's your backcountry excursion.
Oh, that's not that. Yeah, that's the, you don't want that. I can't see sideways. Travel to Jackson Hole right here. I've got to come over. I can't see.
And we've had it. And in the process of going to Cynthia sharing
It's this one.
the agenda screen.
which I would have just covered myself.
Yeah.
Whoops. How do I get out of that? I've got to get under that.
Yeah, let's stop this share here temporarily. Over here. That's the way you get rid of that, right?
Yeah.
Okay.
How are you, Bob?
I know that's not it.
That's not it. Okay, let's get rid of that.
Yeah. Now I need to go back down here and go right here.
Okay. Got it. All right.
Are we ready?
Yep.
So, oh. No,
We're seeing it, but the Zoom people aren't.
right, and they're not seeing me.
Yeah. Okay, so we have to. This is okay. Pull this aside. Go to Zoom. Here. Now we go to share screen. And then we go to find the talk.
Can we just do share?
Well, we have to pick the option.
Yeah, Elizabeth.
I think it's right.
Yeah.
Okay, now,
I've spotlighted
Yeah, I have to
Bob,
put it on play to bring it to full screen.
but I can't, he's starting to be able to show his slides.
Now, if you click on play, it'll go to a full screen.
okay. Okay. I think they're seeing it.
Are you sure?
Are you seeing Bob's screen now?
Okay, he can do side-by-side speaker and then it'll only show him.
Got the talk up.
Cynthia, should I introduce Bob? Are we ready for that?
You are, if the slideshow is ready to play.
It is.
Okay,
And
go
you can
ahead.
see me? Good evening, everyone. Apologies for the technical difficulties. It's a tough marriage we have between Zoom and live. If you do have trouble hearing Bob, don't worry about me. I'm not going to say that much. There are a lot of empty seats over here and you'll be closer to Bob. So if I could ask everyone to please mute your cell phones and no calls for the next hour and a half, sorry. I want to thank the library for the use of this wonderful auditorium. We are very happy to be back in it. I want to put in a plug for joining the Geologists of Jackson Hole. It'll be the best $20 you ever spent. The barbecue alone on July 30th is worth it. Plus the field trips. Mike Adler is planning one to southwest Utah in the fall, and we'll have a few others as well. Before I introduce Bob, I want to honor our president, John Willott, who's been our president for 14 years and is now stepping down, and Cynthia Blankenship, who's our Zoom host, will be taking over that presidency, and at the same time handing the secretarial role to John Guslander, who's sitting over there. Again, one of those things that somebody has to do, and I'm really glad John signed up for. John Willott will be stepping down to vice president, where he will continue to do all the things no one else wants to do. And sorry, that's how it is, John. So John, in recognition of your dedication, your leadership, everything you've put into making this organization what it is, I have a very special present. This is made by our own master woodworker, Brent Schaefer, out of Exotic Woods. And I hope this will have many fine cheeses and bread and crackers on it. John, thank you very much for all you've done for us. And if that isn't enough, there's a map of the wineries in Napa, which we know you will make good use of.
Well, that's the field trip coming up.
Right.
And for all of those that missed the end of April, Colorado to New Mexico. We went through 2 cases of wine on 10 days. So. But thank you very much. Cynthia, thank you. It took me a long time to find somebody with crazy enough to take my job. Appreciate it.
Well, thank
so
you,
much.
John. And I have some wrap for that later.
Okay.
Now I can introduce our speaker. We're very happy to welcome back Dr. Bob Smith, who has spoken here many times, giving excellent and informative talks. I could speak for the entire next hour describing Bob's accomplishments. And in fact, there's a 22-page bio CV that he sent me. I'm going to not read it all, though, don't worry. Bob is a distinguished professor at the University of Utah, geology and geophysics. His bachelor and science degrees were from Utah State, PhD, University of Utah. And just to hit a few of the amazing highlights, and it's sort of like I pick one and then I say, well, what about this one and that one? And again, that would take the next hour. So Bob has taught geology for 53 years. Well, and he's still teaching it to us tonight. He has over 220 papers in technical journals. He has been the major advisor of 70 grad students, launching 70 scientific careers of people continuing to do earth science. He's given thousands, that's thousands of abstracted presentations in national and international scientific and academic venues. He has been the recipient of so many awards. I just picked out a handful, but the other handful are equally impressive. The U.S. Antarctic Medal, the United Kingdom Gold Medal Award for work in Antarctica, John Wesley Powell Award, highest award given by the Department of Interior, George Woolard Award, highest award given by the National Park Service, the GSA, Geological Society of America's highest award, USGS Career Award for work in Yellowstone and Tetons. I could go and do another 15 of these. I'm not. Bob is also the author of a book that I have highly enjoyed. If you want one book on Yellowstone and the Tetons that you can understand, this is the book. And the pictures, the photographs, the diagrams, they're incredible. And you said over 30,000 copies sold and many more, I'm sure, because it's still the best work on this area. Bob has been studying and researching Yellowstone for over 65 years, and he's written the books and the papers that help all of us understand what's going on there. He is truly the voice and father of Yellowstone geology. Please join me in welcoming Bob Smith.
Thanks, Rob. Appreciate that. Well, first of all, I'm not sure who you're talking about, but thank you. Can you all hear me? Yeah. How about that? Whoops. I'm going to use, I've got so many pointers here. Oh my God. Oh, the top. We've got to get rid of that black.
That up there where it says more, the three little buttons.
Say again?
All the way far.
Well, this banner is,
Right,
is on top of the.
Whoops.
More.
High floating.
Control. That's it.
Thank you, Mike.
Yeah, figured it out.
There, can we all see in here?
Yeah.
Take good notes. There'll be a test afterwards. I just want to point out that, whoops, they're back again.
Mike, you're up this time.
Any way to keep this thing off? Because I,
Well, there's also an admit. That may have been. All right, try it one more time.
well,
There you go. Hide floating meeting control.
hide,
Two more down there, right there. Yeah.
but it seems the light to come on
And
its
don't
own.
press escape.
Don't hit escape. Yeah.
Okay, well, anyway, Yellowstone Explained, and a little bit of my Antarctic experience. Some people asked me if I had been in Antarctica, would I say something about it? Yes, I've been in Antarctica, and I've done a lot of research related since then. Now, this thing,
I think every time someone comes in.
So there it is without it. Yeah, so there's the question everybody's going to ask, and the answer is it ain't quite yet. But you can see from the number of newspaper articles, of course, Yellowstone is so vivid in the world's memory about an impending eruption. And I just said at the bottom, don't believe everything you read or hear. Now, one of the things that I've been proud of in my career, I like to integrate things. Integration means I like to understand the processes of how things work. I especially like to understand the processes of geology. And I put up here this figure, which embodies the whole idea of what Yellowstone's about. You've got to understand the hydrothermal systems. You've got to understand earthquakes. You've got to understand heat flow and magma, ground deformation, and it all comes from the mantle. So all of these double arrows here imply the relationship of the entire system. So I'll be talking about the core mantle structure. This is the Yellowstone Plume, the shallower structure of the crustal magma body, and then what happens when we have deformation. We get these beautiful rainbow images from satellite imagery. Oh. Now, just to make sure you all know what volcanism is, this is a system where they pressurized a resin at the bottom of this test tube with acetone, and they heated it up. And when it heats up, gases come out of this, and this is just like a rhyolitic eruption. So you can see as it heats up, these are bubbles that are coming to the surface. You'll see some bigger ones, and when they come to the surface, we have a giant eruption. And so the question is, how do we understand this system as applied to Yellowstone? And it is a good analog model, and just bear that in mind. Well, remember where we're at, up here in Northwest Wyoming. There's the Yellowstone hotspot. But in the context of plate tectonics, we're dealing in the Western US. You can't just leave Yellowstone by itself. So we have the Juan de Fuca plate, which is subducting from west to east. The Pacific plate is deforming along the San Andreas Fault. We have the Basin Range, which is extending. And then we have the Columbia Plateau basalts and the Yellowstone Snake River Plain system, with Yellowstone at the tip of this feature. Now, what's important is that it's within a continent. Most hotspots are, in fact, oceanic. Yellowstone is, in fact, well within a tectonic plate. Now, you've probably seen my picture before, but I like to show it because it does remind us that we're sitting up here on this high mountainous plateau, if you wish. But here's the track of the Yellowstone centers of volcanism back to 16 million years. Now, I don't mean individual ones. Each one of these features has multiple eruptions, up to 150 now that have been mapped. So as I say, if you take the North American plate and let it move to the southwest at about 2 centimeters per year across the hotspot, you burn your way through, of course. That's the active volcanism of the Snake River Plain system and the subsidiary zone off to the northwest, the Newberry Train, which is much smaller in volume. And there are several big dikes, but again, they're roughly 17 million years old. So around Yellowstone is what we call the tectonic parabola. And that's where the zone of most active earthquakes are, shown by the red dots. And this is like a boat going through the ocean, except the ocean here happens to be continental lithosphere. But regardless, it produces the same kind of feature. Now, when people always ask me, what's going to happen in the big one? Well, I put together a lot of early instructions and ideas of what a super eruption might have looked like. This is looking down to the south towards the Tetons. This is the outline of the northeast side of Yellowstone, and the Caldera system, as I've depicted here, very highly depicted, was erupting super eruptions that probably went on for literally months and months, and gases and aerosols got into the atmosphere, completely surrounded the Earth. So, as I said, this thing lasted for weeks to months. These atmospheric features go to 80,000 feet, and they will spread out in the jet stream. Now, people always say, well, Yellowstone erupted out. No, it didn't. Most of it, 90%, came up and then fell back in to the magma system itself. Regardless, it's had a tremendous effect on temperatures. And right here, the climate temperatures we expect were reduced by 8 to 10 degrees centigrade, equivalent to volcanic winters. But they went on for literally months and years. So today, we're sitting down here in Jackson Hole, and I plotted here the youngest of the volcanic rhyolite, Lava Creek Tuff, and it covered this area. It was underlain by a smaller system over here at Henry's Fork, and then Huckleberry Tuff was covering the entire northwest of Wyoming, Idaho, and Montana. Of course, most of it's been blown away and faulted away. But these are the three main features then. 2 million years ago was Huckleberry Ridge Tuff. Henry's Fork Caldera, 1.3 million. It's a small, it's Island Park. And Lava Creek Tuff, 640,000 years ago, was this giant eruption. Well, how big is this thing? I tried to demonstrate the relative sizes, like if you take the Yellowstone caldera 2 million years ago, 630,000 years ago, and you add them together, it's the size of these equivalent 3 cubes. Tambora in the Southwest Pacific, 36 cubic miles. Mount Mazama, Pacific Northwest, 18 cubic kilometers. In Krakatoa, Southwest Pacific, 4 cubic miles. Mount Pinatubo, which we're familiar with, very, very small, 2.4. And Mount Helens, of course, from the eruption in 1980, was actually very, very small, 0.3. Now, this system is depicted here by the ash fallout. And this has been done by coring, by sampling over the whole Western US, and now within the oceans in the Eastern US, and this slide's a little bit out of date. But the Huckleberry Ridge, as you can see, covered much of the Western United States. And then we had, if you wish, the Yellowstone caldera, which is the young one right here, the Lava Creek Tuff, all the way down into the Gulf of Mexico. And you can see the extent of these ashes that covered this entire system. Mount St. Helens was a wee one up here, and actually it was up, deposited ash into the Jackson Hole region, Yellowstone region, up to several millimeters, even a couple of centimeters. But the ash fall, of course, is the major tectonic feature, if you tectonic scale. But Yellowstone has big earthquakes. And 1959 was a magnitude 7.5, depending on the scale. And it ruptured the Hebgen Lake Fall. And that rupture was 40 kilometers long. And it was there's a geology student, three geology students high. That's 22 feet. So that rupture created a large area of ground acceleration, triggered this landslide that came in to the Madison River, blocked the Madison River. And in doing so, we had 29 deaths. Now, you read mostly, it says 28, but I found the 29th in some more articles. Well, 59 is 15 million damage. And over here, even 2005, 150 million. And now I'm sure it's up to 200 million or more. It's a giant, most credible earthquake we've had in historic time in the interior of the Western US. I'm not talking about San Andreas, I'm talking about the Western interior. Well, you all know this probably better than I do. I took a digital elevation system and overlaid it onto a series of INSAR maps. And of course, here's the Teton Range. And as I tell colleagues, especially people who've never been here, we drive north from Jackson, we drive north around the lake, and you get up here, and the mountains are gone. And you drive through Yellowstone, and the mountains don't begin again until you get up in the Gallatins, the Madison Range on the northwest side of Yellowstone. Well, of course, this is because we've had 3 giant volcanic eruptions that have erased much of the topography. So Caldera 1, which is the big one right here, doesn't show up that, there's Caldera 1. It was at least as big as that. Caldera 2, Island Park, and of course, Caldera 3 is right here. The caldera dropped the ground tens or hundreds of meters and formed a giant hole within which, if you wish, much of the later volcanism filled in. And so what you see today in Yellowstone is like a giant toothpaste on the topography. But you're up at 8,000 feet and you're several hundred meters above the background topography, because this is a giant topographic swell. Well, topographic swells are produced because the ground beneath them is hot and uplifting with a hot spot. So if you drive down, here's the road looking north from Old Faithful to Madison Junction.
Bob,
Here's Mount Holmes.
Bob,
Caldera 1 right here dropped the first part of this system, and Caldera 3 dropped it even more. So you're looking here at the boundary wall of the caldera of the last one, the youngest one right here. This is a giant system, and it wiped out the extension of the Mount Holmes area to the south, all the way across the caldera.
Can you use the computer?
What?
Instead of using the pointer, can you use the cursor on the computer? And then the Zoom audience can see it as well as us, if that'll work.
Oh, that's kind of hard. Let's see, where is the pointer on the computer now?
Well, the pointer's fine for us. Right, that may be.
Well, I don't have the pointer up. Well, I think you can see these slides from the other side of the room as well here. This is a picture taken of the rhyolite in the Madison Canyon. And what you see are these look like waffle paste coming down. This is rhyolite. It was molten and it covered the surface. So you can see, whoops, over there. Nah, pushing too many buttons. The point being is that this giant system expelled these large molten flows of rhyolite, which is a generally much more viscous or less viscous than, well, it's more viscous than the basalts, And the actual basalt, you can see them here. These are the basalts you can see.
Just gonna scoop
Now,
this
I
out
asked the
right-
question, why is it always uphill to Yellowstone? No matter where you live or you travel from, you got to go uphill. You got to go uphill. Whoops. I don't know what's happening here. We okay?
Yeah, I just want to plug this into your,
Oh, it wants a little power.
right, want some electrons.
Oh, I think it'll make it.
And if you use your cursor
It
pad,
says low battery.
Pardon? Oh, I've got all these.
wait, this is the power cord.
Right, that's going to go in right here. You just put it in there and let's see if that, you can plug that in.
Electricity.
But I had it fully charged. At any rate, why is it always uphill to Yellowstone? Because you got to drive uphill no matter where you come from. You come from uphill, of course, from Jackson Hole, Snake River Plain, Montana, Cody. So we'll answer that question as we go through the discussion. Now, once you get up into the part of the Yellowstone Caldera, which is the very north end. So this is a picture of the Caldera boundary fault looking south into what is Yellowstone Lake. So this is a large graben. And the fault on the left was offset to the central part by, you can see, 30 meters. And there's some antithetic faults here which dip back. Here is that fault looking from the ground. 90 meters of offset here at Mirror Lake. So if you ever want to go for a nice long horseback ride, 25 miles, you can ride right into that fault scarp and your horses can't go up that face. If you look into Yellowstone in the winter, here's a picture, I don't know if I can get that over there. So this is a picture of an uplifted dome, which is the Mallard Lake Dome, just north of the Upper Geyser Basin. And you can see this uplift. It turns out that uplift is about 500 meters. And when you uplift something that's brittle, it cracks in the middle. And there's a fault zone right here facing the north and one right here facing to the, whoops, to the south. And if you go down in the area of the Excelsior Geyser, the south of Old Faithful, this is that resurgent dome called the Mallard Lake Dome. And these are the two boundary faults that are right here. And that Mallard Lake Dome was expected to have risen or occurred to about 640,000 years ago. Well, I put in some Yellowstone earthquakes because this is big time stuff. And Yellowstone is part of the Intermountain Seismic Belt that I named, by the way, back in the 70s. That zone extends from southern Utah up through the Wasatch Fault. Here's the Wasatch Fault. By the way, it has a seismic gap. And then we get this zone tectonic parabola, and there's also a seismic gap at the Teton Fault. And I'm not going to go into that. I want to show you more of the seismicity of Yellowstone itself. We have the Hebgen Lake earthquake on the northwest side, this zone of east-west seismicity, and we have these zones of north-south orientation of earthquakes. And they are, of course, occurring beneath the volcanic cover, but we expect that these are normal faults that were ruptured 16 million years ago and then covered beginning 2 million years ago by volcanic rocks. Well, I'm happy to say, being a pilot, I was flying in 1984. I was out of fuel and I turned to the left when I was flying toward Madison Junction. And we thought, God, there's a forest fire up there. And I said, no, there's not a forest fire. I got on the radio, no, there's no forest fire. That's an eruption of Steamboat Geyser, the tallest geyser in the world. And I flew right into the mist right here and left. I barely got to West Yellowstone to refuel, but you can see this geyser has at least 400 feet of elevation. So there's hot water. You can see the trees here at the bottom. You can see trees right in here. Those trees are 70 feet high. This was this was boiling water blowing out, knocking down trees, blowing rocks out. And then we have a zone of hot water and then steam and mist. So how lucky was I to take that? I don't know. Someone was watching me. I did calculate the probability. One chance in 150 million. It's about the same as winning the Powerball lottery, by the way. So how do we study Yellowstone? I study it from the standpoint of earthquakes and ground deformation. And over here on the left is our distribution of seismographs. And on the right, a distribution of GPS stations. So we have an array of seismic data that come in to the University of Utah in real time as the GPS data comes in to the University of Utah and also an associated member, UNAVCO. The point being is that this is probably the best monitored large volcanic system in the world. And if you go to my webpage, quake.utah.edu, you can see it in real time, as fast as I can. I didn't put that down, but it's quake.utah.edu, and I'll mention it again. Say again?
The different arrows, the green, blue, and yellow.
You mean here? Oh, they're for different, seismographs come in vertical components and they have horizontal components. And some are shorter period vibrating at higher frequency and some are longer period. So that's what these different colors refer to, the different kind of seismometers. We have 300 real-time channels that's available to you and me. And by the way, you can get it as fast as I can. We set it up so the public has access. There's over 100 GPS channels in near real time. You know how many hits we get a day on this? 5 to 10,000. And if there's a swarm of earthquakes or something political, get 10 to 20,000. Because the world is watching Yellowstone. Most of our hits come from Asia and Europe. The people around the world are watching Yellowstone as well as we are. Well, as I mentioned, we've got this east-west zone of seismicity, magnitude 7.5 up here at Hebgen Lake. But in the 75, we had a magnitude 6 by Norris geyser basin. So this zone is very active, and I plotted in here. There's a little, I'm sorry, you guys can't see that. Yellow stars are the volcanic vents that occurred after the last super eruption. And there's about 60 of these yellow stars. You can't see them very well, I can't either, except they align themselves with the earthquakes. So these volcanic vents are associated with structures that are seismically active. You can see them right here, almost down to the Teton region. Well, when we get big earthquakes, here's what happens. As I told you, 3 students high, and I want to put this in because the rocks came down into the Madison Canyon, as you can see. And these 2 guys are Charlie Craighead and his brother in 1959. Now, you all know Charlie Craighead. So these are pictures that, you know, the road is closed, but this family was working, of course, in Yellowstone with their father and their uncle. Now, one thing is that this diagram is I took these are the faults that ruptured in 1959. And the area in blue is where you decrease the stress. So the fault rupture decreased the stress and the ends increased. And we call this the dog bone pattern. And you can see that the dog bone pattern is where all the aftershocks are. Whoop. And the earthquakes themselves extend into this zone of high stress. That's the area in red. So the earthquake activity in Yellowstone, this whole broad zone up here, is not related to the Yellowstone volcanism at all. These are aftershocks of that 1959 earthquake. And these aftershocks are going to go on for hundreds of years. Now, the zones to the south are, in fact, the ones I mentioned before. These are related to the basin and range faults that are now covered by the magmatic system of the inner caldera. I had the fortunate experience in 1956. I was hired by the Fish and Wildlife Service. I was a GS0. And what that did, they sent me all over the place in Yellowstone. I went everywhere they didn't want to go. And this is Peel Island. Anybody here been to Peel Island? It's the very south end of the south arm. And you can see there's the end. There's the old boat dock. It's covered by water now. And the reason is that the lake is tilting to the south and it's killing all the trees. And it's upraising the beach at Fishing Bridge. So it's a bathtub tilting to the south, something to the north in the central part of the caldera is creating this. We got pretty excited in 75 and we went up and started making very precise measurements of the ground elevations. And fortunately, when they built the roads in 1935, 34, they put benchmarks in. So we went back and we occupied, these are some of the benchmarks that are on the ground. And we measured the height of the deformation. And we compared it from 1977 back to 1935. And here's what we discovered. We discovered that if you arbitrarily say it's 0 down here at the south end of the caldera, and I've contoured these in millimeters, the central portion of the caldera rose 750 millimeters. That's 75 centimeters, almost a full meter of uplift. So this is a giant system that's gone uniformly from north to south over a distance here of 50 or 60 miles. So if you take a point measurement at the height, which is in Hayden Valley, compared down to here, again, this is the bathtub ring creator. If you uplift the caldera, then Yellowstone Lake tilts down to the south. So that's what we observed from independent data. Well, of course, we got into the domain of GPS in 1987, and you probably have all seen GPS, et cetera. We have GPS stations in an antenna with an invar steel rod that's drilled into the bedrock 1 meter. Now we have a collar around the side, around the bottom part, so the animals won't tip it over. What's amazing about our new GPS data, we can measure the accuracy of these instruments within a few millimeters. And I can measure the accuracy, this happens to be the Sour Creek Dome, with respect to anywhere in the world that has GPS. This is putting in a portable GPS instrument in the what's called the upper geyser. This is the Hot Springs Basin. It's the most beautiful and the largest hot spring system in Yellowstone. And it's clear to the north of Fishing Bridge, say 25 miles. And in the background, you can see that Caldera bounding fault. But you can see this whole zone of hydrothermal alteration. And we put our first GPS instruments there in 1987. And these are portable, so we could put them in, leave them for a few days, take them out. And then we use primarily helicopter support because we had so many of these, we had up to 60 of them. Now, I'm just showing you here the deformation measured by GPS. Now, this is years, starting back in 2002, to the right up to 2020. And these are stations, the top ones, White Lake, Lake Wyoming, Old Faithful, these are all inside the caldera. And these, big thumb. And these stations are all outside the caldera. But look what happened. Over that period of time, we've had uplift that you can see here of upwards of almost a meter, 3/4 of a meter. Within the caldera itself, outside, not much going on. Now, in 2014, we had an earthquake right here. And after that earthquake, the ground has started to go up very fast. We don't know what's causing it, but it's part of the dynamics of this active system. So if you plot the number of earthquakes here, sorry, if you plot the number of earthquakes per quartile, that is, 4 bars per year, starting back in 1923 when they actually put those road points in. This is the number of earthquakes per quartile. And then as we got better and better instruments, the numbers got bigger and bigger. And we started to discover that most of the seismicity are in earthquake swarms. Ground shaking is related to earthquakes that are closely located in time and space. But if you plot the deformation, starting here, the caldera was going up at 1.4 centimeters per year, 2.2, and then bang, we had a magnitude 4.8 on the northwest side of the caldera, and it started going down, then up and down. And then this last period of really high uplift, 2010, 2014. This was a big earthquake swarm, and we think it was basically the earthquake was the result of uplift produced by magmatic intrusion. And then we had this earthquake, and then fluids, magma squirted out the sides. So outside the caldera, look, the caldera is going down, outside's going up, down. They go in sympathetic motion. And the reason is you're moving magma at relatively shallow depths. Well, we actually measured the actual magmatic flow. This is the area of uplift, and we measured the Norris area had some seismic. So this area was pushing fluids into the magma body, and there's a cross section. So it's earthquake. So this is a cross section from northwest to southeast. And you can see the depths here down to 10 kilometers. Here are the earthquakes that are triggered by the fluids coming in the side, squirting out the side, creating the dog bone diagram, but now in vertical space. So we have an inflating sill of magma and a deflating, if you wish, area around the Norris Geyser Basin, just at the end of the northwest side of the Caldera rim fault. Well, the controversy of Yellowstone is this. Is it a plume or is it a plum? I bring this up because this has been a big topic globally amongst geoscientists. Well, we didn't have any instruments to do the kind of tomography I'm going to show you. So the question, did it come from the core mantle boundary, 2,800 kilometers deep, interact with the lithospheric plates, or is it a very shallow feature? I call it a plum. Well, I'm going to show you what I think. First of all, I want to remind you that magma systems follow the physics of lava lamps. Now, when I say magma in these systems, don't think of 100% melt. It's only about 10 to 20% of molten rock within a highly fractured, if you wish, network of rocks. So, but think of it, you have a heat source here, you have wax here, you have a different kind of a fluid, and of course, buoyant, when you heat this up, it gets lighter because the temperature is increasing. Now, I have one of these on my desk at my house in Moose, and I was going to bring it, but it was too hot to handle. But it's the same feature and the same physics. Well, what are hotspots? These are the ones I've known about. You've probably known about Hawaii, and you've known about Yellowstone. Iceland, you're probably familiar with, but look at the rest. There are hotspots throughout the Pacific, along the mid-oceanic rises in Africa, Indonesia, and the Southwest Pacific. These are very, very active systems. But I said, well, the Yellowstone hotspot, as far as I'm concerned, is the American hotspot, because that's the one we have. Oop. Now, what we do is we put seismographs on the surface. These are seismic stations along the surface of the earth, and we have an earthquake, and it sends up seismic waves that propagate at 6 kilometers per second. And if they go through solid rock, they go through faster, but if they go through a melt, they go through slower. So slower is hotter. And this is the big array that we started in the 80s and 90s. We put seismographs around the entire hotspot, not just Yellowstone, but around, as you can see, extending clear into Montana, Snake River Plain, as far south as Pinedale, because we wanted the breadth to see how wide this thing was at depth. So our width is 400 kilometers, as you can see. So we can see roughly that same depth or better. Now, what we discovered, this is an image or a series of images. Remember, red was low velocity and hot. Blue was higher velocity and solid rock. So at a depth of 80 kilometers, you start to see this red body emerge. And you get down to 180, it's getting bigger and bigger, and then it starts to die out 400 kilometers. And if you map it, you get this low velocity body beneath Yellowstone that extends down as a tilted plume, not a vertical zone of magmatic systems. And the velocity reduction, this one right here, is, as I said, about 15% of actual melt. So that's a hot spot at depth. That's what it looks like. So there's the body tilting down to the northwest. And the bottom of this hot spot, if you wish, 650 kilometers, is beneath the Idaho-Montana boundary. It's not beneath Yellowstone. Everybody said if you had a plume, it goes straight down. No, it does not. And here's looking in the southwest northeast direction. But this body is very well defined. And there's an image of it tilting down to the northwest. The low velocity body is basically the outline here in this isosurface. Everything within that has about 10 to 15% melt, not 100% like it's depicted in most cartoons and public things. And if you look at it in cross section, this is taking very shallow, 2 kilometers, 5 kilometers, 8, 14 kilometers. Now you start to see low velocities near the surface, and they concentrate as you get down to 5 kilometers, 8, down to about 14, and we lose it. And this is actually a map of that low velocity body. That's partial melt. It's a crustal magma reservoir that begins down south of Old Faithful to the northeast, and at its strongest up to the northeast side of Yellowstone, the Sour Creek Dome. And this body comes clear to the surface right here, which happens to be Lamar Valley. Now, it's not magma here, it's hydrothermal fluid. This is partial melt magma, but up here it's hydrothermal fluids that are very, very close to the surface. Well, this is putting all of our data together. We have a mantle plume that's moving. Here's the lithosphere moving to the southwest. Magma basalt comes through the uppermost mantle, and they occur in a body which is basaltic partial melt. I just showed you this one, but we didn't discover this until only a few years ago. So we have a dual crustal magmatic system, lower crust and upper crust. And it's all moving southwesterly. Okay, this is brand new stuff. So I'm going to show you stuff no one's seen yet. We now use what we call nodal seismographs. And here's one that's about the size of a quart jar. And they're autonomous. You just go out, stick them in the ground, and leave them. And they have a GPS inside of them. They can have two vertical component or horizontal components. And this project that we were just working on was the University of Utah, University of New Mexico, Park Service, NSF funded, and the Brinson Foundation is the foundation that funds us. So it's a brand new image, just taken last year. Now we send data, by the way, some of our systems to Sawtell Peak. That's the big peak west of West Yellowstone, the big radar station. There's the radar station. And we send our data. These are our antennas. We send data from all of our seismographs. And we have, of course, a big electronic system that we have to maintain. Here's what they look like in the field. This is up around the north. This is up around the northeast entrance. Parker Peak is the north side of Yellowstone. But you get the idea. There's a solar panel. The seismograph is in this barrel with an amplifier and radio system, and we transmit the signal from this antenna, and there's a little GPS receiver on top. So we see seismic data and GPS data. Now, here's your oil company guys. Last year, we got funded, and we brought in a vibrosize. How many here have seen vibrosize? You oil company people. There's a vibrosize, and we ran it throughout Yellowstone last year, but we only ran it at night, after 10 o'clock at night until about 6 in the morning, because there's so much noise from automobiles, it would really disguise our signal. but this is a vibroside, oops, that vibrates up and down. It's actually vibrating. You can actually see some of the electrons. So the ground goes up and down at about 10 cycles per second to 60 cycles per second. So it's a source of energy. It's non-destructive, and we can record it and repeat it. And when this truck goes through a sweep, we move it 50 feet to the left, do it again all night and all week. And here's what we discovered with that newest tomography. Here's the low velocity body using some of the limited data we had before. And here's with all those little seismograph stations with the vibrosides. Now you can really see the low velocity body beneath the Sour Creek Dome and the up here just north of Old Faithful. This is the magma system. It's now we're getting very precise images. Well, people say, what do you mean you're imaging? This is just like your glasses you're wearing today. We use the same physics of mapping the rays as you do in mapping light through glass, for example. And I showed you before, these are the low velocity bodies. I didn't mean to repeat the slide, but I want you to understand Yellowstone's underlying by this magma reservoir. It's not 100% melt, maybe 50 to 20% shallowest in the hydrothermal system, Lamar Valley. But if you take it all the way down to the core mantle, down at 2,500 kilometers, that's the outer core. Here's Yellowstone. We mapped the low velocity all the way down the Snake River Plain to the west coast. You can see that body, but this is the body we mapped then. This is the plume, starting at the core mantle boundary. So what actually happens is fluids come off of the core mantle boundary, but the Earth's mantle is rotating at about 5 to 6 centimeters per year. It's viscous. So fluids don't come straight up. They get caught in the mantle convection cell, and over at the surface, they dip, or they turn completely and shallow out at Yellowstone. So Yellowstone's source is not here, it's over here. Basically the west coast of the United States. So what's happening is fluids come up and then they dive beneath the Rocky Mountains. So here's partial melt and then getting cooled beneath the Rockies themselves. And if you plot these data in a map view, here's Yellowstone. This magma system goes to the southwest and it spreads out way beyond the extent of the Snake River Plain. So this plume is coming up. It's rising vertically, a few centimeters per year. The North American plate is cold. That's purple. It shears off the plume. It's just like a candle. Light a candle and pass your hand over it. You'll burn a hole through your hand. It burns a hole through the lithosphere. So basically, what's happened is we've got a free surface, topographic swell, the plume rises up, and then the sides collapse. And I just made a diagram here through this model. What's important is here's the plume in the Snake River Plain. Here's the Teton Fault. The Teton Fault is intimately related to the edges of this system as the whole plume of the Snake River Plain is collapsing. So you're not out of it. Now I'm going to show you this latest studies. Again, we put out these nodal seismographs. You can see where we are. Don't tell people we did it. We do this after the park closes. November 7th, we put out these seismographs, as you can see. These are those portable seismographs. and we run them until the snow covers them. We can put out as many as 600. This one right here has about 200. So we cover, here's Old Faithful, here's Upper Geyser, this is Gibbon Hill. And this is the Old Faithful edifice right here. And this is the infrastructure. There's the road, if you wish, on the northwest side. Now, what we found out was when Old Faithful goes off, there is no seismic signal. That caught us by surprise. So this is Old Faithful right here going off. What we have is a preceding period of time, 20 minutes to 30 minutes of ground shaking. We call it harmonic tremor. So we can map this harmonic tremor, and when it dies down, we can predict when Old Faithful will go off. But Old Faithful doesn't have a seismic signal. It's a very, very weak dynamic system compared to the fluids that are in the shallow part of the crust that are filling the reservoir for the system. You go up on Geyser Hill, these are seismic records. You can see these are for different stations. And about every 30 minutes, it shakes, quiet, shakes. And that is a picture of Geyser Hill and the spring system. It doesn't erupt, but the water comes up to the edge, shakes and boils and steams and goes back down. So it's an active hot spring system. And what we really discovered is that here is the outline of the Yellowstone hydrothermal system. Here's Old Faithful. And to the northwest is this fractured body of hot water and steam. At the very edge is this little thing called Old Faithful. But beneath, clear over to the north, excuse me, the southwest, is the actual hydrothermal reservoir. Fluids come in from the sides, that's groundwater. They fuel this system. And this is the system that actually is the source of the Yellowstone Old Faithful. Here's Old Faithful. There's the boardwalk. Old Faithful Lodge, the Old Faithful Inn. Guess where it is? That's the body that feeds Yellowstone. It underlies the Old Faithful Inn. Now you think that's really unusual. The geologists have actually mapped a dozen of Old Faithful size cones in that area. And you go out, you can start seeing these circular cones. They're old Faithfuls. And we're seeing one now, and it will die off. And we'll have a new one because we have to get rid of that fluid somehow. Well, we went back up to Steamboat, put in instruments, put in these nodal instruments. Now, what we found is the ground shaking was starting down here at about 80 meters, and then the fluids rose up. So think of this as a ball of hydrothermal fluids. Starts down here, rises vertically. As it rides and it drops, when it completely blows out the system, the ground stops moving and then it starts over again. So this is pre-eruption, post-eruption, and you see this time right here, we can predict those within literally minutes or less. So we can predict Old Faithful eruptions, but we don't tell the public that yet. Here's a cistern pool. It's one of these pools. It's underlain by a system that, and it drains. Let me get past that. Okay. So there's two noisy sources, one here and one here. So these are the fluids rising with time. So here's the hour marked, and you can see there's two bodies that are shaking, if you wish, because fluids are coming up. And what's happening is fluids come from this hydrothermal flow off of this fracture system and then to the surface. So we can get pretty good at predicting that time. And that's what they'll look like. So we create a tomographic image, and there's one to the southwest, one to the northeast. And these bodies go down about 100, 200 meters. There's one to the north and one to the southwest. Now, these are low velocity bodies. These are not magma. These are hydrothermal fluids that fuel the geysers. I'm going to go on here. Back in 1984, 94, I was walking along Biscuit Basin, and guess what happened right in the back of me? That's an eruption in Biscuit Basin. And these are rocks. Some of them we recovered later. There were several, they're big features. The Yellowstone hotspot causes a cold spot. You know that. You have to pay your heating bill. So here's the Yellowstone ice cap during the Pleistocene. It covered the hotspot. And when that feature, of course, melted away about 14,000 years ago, and of course left us with the Yellowstone system itself. Now, what's interesting is the hotspot buoyancy caused the uplift, and the uplift caused the low temperature. So if you look at mean global temperatures in this area 3 million years ago, it really got cold, as you can see, up to 12 to 15 degrees cooler, and then 16,000 years ago went back up. So a hot spot causes a cold spot, contrary to our thinking. I want to put this in because I've outlined here the outline of what we call the Yellowstone geoecosystem. And I worked very close with Rick Reese. Rick passed away a month ago. He's kind of Mr. Yellowstone himself. And we put together data around the uplift of the Yellowstone hotspot, and that's this purple line. So the general topography of the hotspot today is outlined by this purple line. It's the Yellowstone Plateau all the way down into south of Teton Valley, south of Jackson Hole. So this whole feature is a result of, if you wish, uplift, and then the very uniqueness of the ecosystem itself is outlined by the magma system. Now, I've got a whole talk on relationships of geoecosystems. I'll probably have you guys here. This is a lot of people come around faithful. And what we did here is we plotted all the people walking. Here's the evening, night, people coming up and down, walking around here. You know what the lines are? Well, they correlate with number of toilet flushes in the Old Faithful Inn. That's societal. So there's our vibrosize, and I won't go into that. I just wanted to finish off here. This is something we did last year, and we're just repeating it now. We went into the Upper Geyser Basin, and we put a camera right here. It goes down in to Doublet Pool, and here's what we discovered. We discovered this gurgling hot spring system. And I have some other pictures. There's also all kinds of bones and animals that have fallen into this system. But this is the kind of measurement we can make now, both an image as well as the seismic signal. So that's brand new. They're working with people at Berkeley as well. Well, I'm going to just finish off here and say, what's the biggest hazard in Yellowstone? I'm talking about geologic hazard. Caldera eruptions are over here. That's 0.0014% of the pie. If you put it in terms of annual risk, There's the pie. There's the super caldera eruption. Don't worry about it. Your insurance salesman won't care. Post-caldera flows like we've had in Yellowstone, they're still very small, 2 to 3%. Large hydrothermal eruptions are very high because you're out there walking amongst all of the features, but they're not big. There's what's big. Earthquakes. Earthquakes in Yellowstone dominate the geologic hazard, as they do in the Teton Fault, the whole Intermountain region. So this is where you pay your attention and pay your insurance money. Well, there's that plume again. I just wanted to show, this is some of the newest data. I told you that low velocity body extended up into the Lamar Valley. That's the outline of that body. This is Lamar Valley up here. The caldera is cleared out to the southwest, but the low velocities clear up to the northeast. And we even actually think it's further north beyond Lamar Valley, up by Soda Butte. So next time you're at Soda Butte, you're over a magmatic system. Now it's about 4 to 5 kilometers deep, so don't worry about it. Now, people ask me last month where I've been in Yellowstone. I've been in there 65 years. And I made a map of all the places in the backcountry. So here's the caldera. The roads are these little things here. But these are all the places that I've been in the backcountry of Yellowstone: Central Plateau, Pitchstone Plateau, Mount Sheridan, the Thoroughfare. I've been everywhere in Yellowstone. I had the fortunate capability and job to actually map all these systems, particularly when I was younger. But last month, they did recognize my longevity. And at this latest meeting, I received this plaque. It's called Expanding Yellowstone for the Next 150 Years. And I got that notoriety, which I don't deserve. But by the way, it's on a piece of wood, not metal. So my advice to you is visit Yellowstone before it visits you. Now, you guys can leave. I've gone over my time, but I've got a few Antarctic pictures. If you like things that are exciting. I was a lieutenant in the United States Air Force, class of 62G. 18 months later, I was called by Secretary of State Dean Rusk's office to go to Antarctica as the exchange scientist with the British Antarctic Survey. And there I am, driving a dog team. I've 18 months after I was flying this jet, I was driving this jet. That's Antarctica, at Halley Bay, where I was. Now, if you don't mind, I'm going to show you a few pictures of a fantastic place. Not much science right here, but I boarded a ship, came down to the Falkland Islands, down along the Palmer Peninsula, came back out here, South Georgia, down here. I went all the way down here to Halley Bay. And that's where I was stationed for almost a year. And then I was with the British Antarctic Survey, not with the US system. There's the ship that we brought in. That's what it looks like. Beautiful mountain block. This is part of a rift valley. Normal faults is like Teton Fault. Big glaciers coming in. Cumberland Glacier, one of the biggest glaciers in the entire world, comes in at South Georgia. There we are unloading. These are old pictures. I did this in '63. We're unloading, as you can see, we had a farm-all tractor. We're unloading gear from that ship. We got onto a traverse. We went inland for about 100 miles. Now, these are Bombardier snowmobiles. Average temperature in a warm portion of the day was 40 below. Cold part of the day, 50 to 60 below. There we are. We have to, once you start these snowmobiles, you can't turn them off because you're never getting started again. So we carry a lot of fuel, refuel them continuously. I'm showing you that. There I am. I'm showing you that because this is an Adelie penguin. See that right there? It's a leopard seal. Leopard seals are mean. And I got bit by one. Going down the Bransford Strait. Here's doing geologic mapping. These are dolerites. Notice our transportation. We were still using dog teams. We had access to snowmobile, but when we got onto the ice, they were too heavy, so we used the dog teams. Now, this is my adventure. We had crossed a crevasse. See these ropes? They go down. The base leader was with me. He went all the way down to the end of his rope. I went down on the other rope, down to my armpits. Turned out I broke my ankle. He got a camera out of his parka and shot up. Now he had a compound fracture. He was a doctor. We got into the surface, put him back on here and shot him full of morphine and got the hell back out to Halley Bay where we actually did operations on him. This is some of the, these are Greenland Huskies. They weigh 150 pounds. They eat 10 to 20 pounds of raw seal meat a day. Emperor penguins by the literal hundreds of thousands. This is a rookery just south of where I was working. And when you walk out into them, they all move apart and they sit there and watch you. And as you walk along, it's this moving hole. That's these guys are watching saying, where did you guys come from? I was a pilot. And I was given the chance one day to fly on this British Bombardier. This is a de Havilland Otter. Now, I was a pilot, and they invited me to fly. We were going to fly from the northern Palmer Peninsula way down onto the ice. When we say the ice, that means the continent. I got all bundled up in all kinds of Antarctic gear and everything. I walked out to the airplane, and pilots walked out in street clothes. I said, what the hell's going on? We're not going to fly 600 miles south. The back part of this airplane is extra fuel tanks. They said, if we go down out there, we're done anyway. So we might as well be comfortable. Needless to say, I kept mine on. There's one of those leopard seals that bit the back of my leg. I've shown you these before. Now this is an interesting story. I was down on this, I was on this little ship right here. We got frozen in on the west side of the Palmer Peninsula. And we were frozen in for a few days. And the crew came to me and said, Lieutenant Smith, are we going to stay here long? And the captain said, yeah, we got enough food for a year. I thought about that for a couple of days. Wait a minute, I'm not staying here for a year because we're frozen in. So I got on the radio telephone, called back to Secretary of State Dean Rusk's office and said, this is Lieutenant Smith and we're frozen in. And I got this message back, just cool it for a couple of days. I did, and I waited and I waited. Suddenly out of the north comes this ship right here, the USS Glacier, the biggest icebreaker in the world. It's nuclear powered. It sailed down, circled us, and we followed him out. There was no communication. We were not allowed radio communication because we didn't want to embarrass the Brits. That's the Brits, that's the Americans. That was pretty exciting. Kind of finishing off here at South Georgia, there is the grave of Sir Ernest Shackleton. There's where he is buried. Sir, you've heard of Sir in the Shackleton, I presume, in your history. He went to Antarctica 4 times. On his last voyage, he came back to South Georgia, had a heart attack and died. And he's buried right there. Now, after all this, I was given the US Antarctic medal on the left and the British Antarctic gold emblem for this service and for what we did. And I fully appreciate that from the Americans and the British. And let me tell you something, but you know where I have the most fun? On horseback at the thoroughfare. You guys been to the thoroughfare? How many been to the thoroughfare? Oh my word. It's the most beautiful place in Yellowstone. Southeast corner. That's the thoroughfare cabin. This is a ranger I've worked with for 40 years, and I'm riding that beautiful horse. It's a 38-mile horse ride, by the way. You don't get used to it, it gets kind of rough. So that's the end of my presentation, and I appreciate folks coming here, and I'm happy to answer any questions or give you any advice. I'm sorry it's a bit long, but I thought you'd want to see the Antarctic stuff because people have asked me about it. When I turn the
Well, so we're going to take questions from Zoom and from here. Why don't we start with like 2 questions from here, and then we'll go to Zoom. So somebody have a question? Bob?
say again.
How has the improvement in the data collection, for example, time, number of stations, frequency, improved the resolution of your
A seismograph
so Bob,
array is
I
like
need
an
to-
antenna.
I
So
need
the
to-
wider the antenna is, the deeper you see. So
I'm going to repeat the
I'll
question
come
for the
over here.
Zoom.
Yeah, so if you make this antenna, it's like a glass in your eye. If you make it stronger and more fine, you can see things more detailed. It's exactly what the seismograph array is. Seismograph arrays I showed you were up to 400 kilometers wide. So they're a bit wider, but we put in upwards of 600 stations in some of those arrays, and that's where we get the resolution. Any more?
For Cynthia, is there a Zoom question?
Yeah, we have one Zoom question. Bob mentioned earlier that based on your seismograph array or other sensors, when Old Faithful will erupt. Why wouldn't you tell the public if you know when it is?
Well, this is very
So, Bob, you have to
experimental
report.
and it's new information. And we haven't refined the methods of the data well enough because it varies by tens of minutes. But we know the answer is we will probably in the next couple of years start well, the data is online if you know how to interpret it, but we haven't released it yet because we haven't really refined the method so that the public has trust in us. We cannot have a failure. We want people to trust what we do, and they want us to be reliable. So that's why that's being carefully looked at.
And one more from chat. How was the 300 degrees Celsius temperature of Steamboat source calculated?
The temperature of Steamboat.
I thought
Well,
it was
first of
high-
all, we
it was
have
high.
an image that goes down into the geyser itself. So we actually get a thermal gradient. Now, the bottom of the system, we could only go down, as I recall, 80 or 90 meters, but we extrapolate the temperature down because you get into a convective body. It's not exploding. You're into a steady state body. And so we extrapolated it basically on the basis of the thermal gradient that we measured. Now, that's a linear interpolation, but that's all we can really do. But it's probably not far off. Now, it's hot down there, but it's not magma. It's a hydrothermal body. It's like basically, it's a big boiling pot. But once you get below the top of the boiling pot, the fluids are in very small convection cells. And I have images of all that. I just didn't want to show them to you yet. I mean, I've got them. That's another day.
So I want to close by saying July 19th, a great program on the Green River Formation. And I want to thank Bob, a small gift from the
Oh.
geologists of Jackson Hole.
Thank
It's
you.
fragile, don't drop it. Thousands of years old.
Oh,
And
wow.
again, if we could give Bob a round of applause, and then if I could get the chairs on this side move this way and the chairs on the other side move the other way. And Bob can answer a couple of questions.
Yeah,
if
I'm up here
there's something
trying
you
to
didn't wanna-
disentangle all this.
Oh, we'll take care of that.
No, I get
Great job. Thank you.
So Bob, you're getting kudos from the Zoom audience as well. Thanks for a great presentation.
Thank you very much. It's fun to do it for you guys. You're always interested.
No problem.
I do have a couple more Zoom questions. I don't know if you have questions from live there.